Okay. So also I'll leave, so if you have questions regarding the quiz, problem sets, make sure you come talk to me or the TA, okay, this week. 19, yes, April 19th, which is this Friday. So okay, so last time we started bipolar junction transistors, and we'll review the key points and then try to finish up whatever we need to know, okay, in chapter 7 today. So bipolar junction transistors are different than MOSFETs because they involve the diffusion of both holes and electrons. That's why they're bipolar. Okay? Both types of carriers are involved in the transport. Whereas in MOSFETs, only one type is involved. It's either N channel or P channel. Okay, so that's a key difference. Other than that, the physics is very similar. Once you start, well, the physics is different, but the current voltage characteristics are very similar. Okay, so keep that thing in mind, and let's take a quick look at what we saw. I'll skip through this part. Okay, so this is the basic idea of the bipolar junction transistor. It's shown here. So in the current voltage curve, so the current voltage curve is essentially a reverse bias PN junction. Okay, and the only thing that's changing is the reverse saturation current of this PN junction. So as you increase the hole injection, you're changing that reverse saturation current. And by our good understanding of the PN junctions, we know that the reverse saturation current should be independent of the reverse bias voltage. Okay, so you have a saturation operation, which means that now you can use that as a transistor. You have amplification and you're switching. Those are the two things for a transistor, right? Okay, so in a bipolar junction transistor, of course, the whole current injection comes off because you have a forward bias PN junction. Injection is a majority carrier injection in a forward bias PN junction. Okay, so to review, the structure looks like that. Okay, so this part is the reverse bias PN junction on the right hand side, where you have a collector base. Okay, that's reverse biased under normal operation. Then you have emitter base, which is the whole injection part, which is forward biased. So think about this PN junction first, which is reverse bias. You have a reverse saturation current flowing, which is independent of the reverse bias voltage. Okay? And that reverse saturation current can be controlled by hole injection from this forward bias PN junction. And that's the picture. That's a qualitative picture. You need to understand that. Okay? Of course, the details are a bit more complicated. Okay, and we'll look at those today. Now, the key parts, of course, to keep in mind are the input, output, and control of such a bipolar junction transistor will depend on the configuration. So we have to be careful how it's used. Okay? In this case, it's a common base configuration where the base terminal is common to the emitter and the collector circuits. Okay, it's called a common base configuration. In this case, the current that is controlling the amplification is the emitter current in this particular situation. Okay, the emitter current is what's doing the whole injection. And the output is the reverse saturation current of the base collector PN junction, which is this current, IC. Okay, that's the reverse saturation current which goes up and down on the curve. And the input signal where you put on, it can, if it's an amplifier, the input signal goes into the control, right? Goes into the emitter current. Or it can actually be the voltage here, the base collector voltage I showed you. That's a bias. You can think about that as a bias voltage as well. Okay, if you're an amplifier, you have bias voltage and then you have a small signal right input, right? And you get an output which is a larger signal. Okay, that's the idea. Of course, we can also have the common emitter configuration, which I think we talked about last class. Okay, we'll come to that. This picture is probably one of the most important things that you need to keep in mind, because this will allow you to understand how the current is calculated. Okay, and we'll look at this today in more detail. But let's go through this quickly. So again, you have the base, collector, emitter, and if you look on the right-hand side, it's nothing but a reverse bias PN junction. Okay, The base and the collector are reverse bias p-n junction. When you have a reverse bias p-n junction, the only thing you have to worry about is reverse saturation current. Okay, and that is just because of minority carriers getting extracted to the other side, right? So in this case, you have these two small current components. The electrons extracted from the p-type to the n-type, the minority carriers extraction, and the holes going from the n-type to the p-type. Again, minority carrier extraction. Very small current, almost zero. Okay. Of course, when you add this side to the p-n junction, which is hole injection, in this particular case, the situation changes. Now you have a way to control that reverse saturation current. Okay? So to understand that, of course, it's very straightforward because this is a forward bias p-n junction. When you have forward bias p-n junction, you have majority carrier injection. Okay? The energy barrier here is lowered, and the electrons get injected across. Holes get injected across from the p plus to the n-type. And if those holes can make it across the base, then it can form part of the collector current. That's the idea. You make the base very small such that the holes will basically diffuse across without being lost by recombination. Okay? So that's the main thing to understand. Everything else is kind of parasitics and so on. So keep that picture in mind. So by controlling how many holes I can inject across this junction, I can control what that current is, almost independent of the bias voltage of that base collector junction. Okay, that's it. That's basically the fundamental picture. Of course, there's some details which we also need to worry about because we've ignored a few things. First of all, of course, when the holes get into an n-type region, they have to recombine because they see lots of electrons, right? They have to recombine. Although we try to minimize the recombination, it always happens. Now, of course, when they recombine with electrons, those lost electrons have to be compensated. They have to come from somewhere, and they come from up here, the base terminal. And there's a little bit coming from here, but that's too small, so the base terminal. Okay, and those electrons will recombine with some of these holes, which is this one here. Of course, because this is a forward bias junction, electrons can flow the other way as well, n-type to the p-type. So you have a little bit of an electron flow that way. You also try to minimize that. So you have these 5 components of current, which you should be at least conceptually very clear about. Okay? That's all you really need to know. Everything else is are details. And did we finish this? I forgot. Did we do this example? Okay, you did. Okay, so go back home and make sure you do this again. Good. Because as long as you're able to do it yourself, I'm pretty confident you will be able to understand the operation of the device. Yes?
So IC is always less than IE, right?
Yes, that's
so
correct.
When you're trying
yes.
to do amplification, then do you give the signal to the IC end?
No, to the IB. IC is always, so the collector is always the output. That doesn't really change. The control can change. The control can be the emitter, as I've shown here. Okay? Then in that case, you're absolutely right. Remember we talked about this? The gain from the emitter to the collector. Do we remember that? IC divided by IE. Okay? This was defined as gamma times beta. Right? And this is always less than 1. Because each of these terms are less than 1. Gamma being the hole injection efficiency of the emitter current. What's a fraction of the holes that make up the emitter current? Okay? And beta being the probability those holes actually make it to the collector set. We'll revisit that soon. Yes?
So the current will be less
yes.
in IC, but the voltage across there, like the voltage output on your resistor can be higher than the voltage for the control.
Actually, let me step back a second. But if you use the common base configuration where the small signal goes into the emitter, you do not get amplification at the end of the day. That's the answer. If you want amplification, you need to send your small signal to the base and have a common emitter configuration, which is where we stopped, I think, last class. Okay, we'll come to that in a second. It's an important condition. It's easier to understand this picture, but the actual operation is different. So this is what I was talking about. So let's very quickly see what this means. Okay, the collector current is some proportion, some B times the whole component of the emitter current, i.e. P. Okay, and that B essentially represents the probability that the hole that comes across from this junction makes it across to this junction. Okay, that's a probability that it does not recombine. That's the idea. Okay, so that's a whole component of the emitter current. That's a base transport factor. It's a fraction of the injected holes that makes it across the collector. Okay, then we have to define a hole injection efficiency from the emitter side, which is essentially the fraction of the hole current divided by the total emitter current. Okay, so basically it is this component as a fraction of this plus this. Okay, the forward bias P injection. Okay, so the emitter to collector, so I just wrote here, is essentially the current transfer ratio, which if you use this configuration as the amplifier, that's the transconductance. Okay, it's essentially B times gamma is defined as alpha, and since B and gamma are both less than 1, alpha has to be less than 1, so there's no amplification. Okay, right? That's not really an amplifier. Now, in an ideal BJT, we can do amplification by looking at the base current, as I said just now. So again, just to review. The base current from Kirchhoff's law is essentially this is just from, not from Kirchhoff's law, but just looking at what should the base current provide. It should provide for recombination of the holes here, and it should provide for electron injection here. 2 components. So that's IEN is the injection of electrons into the emitter. It's the electron component of the emitter current plus the recombination with the holes. 1 minus B being the probability that the holes become recombined with electrons. Okay, so you have those 2 components. You add those up, you get the base current. Now you can define a collector to base transconductance or amplification. And you can see, we did this last class, you get an expression which looks like that. Alpha divided by 1 minus alpha. Okay. Since alpha, in principle, can be close to 1, this factor can be rather large. So you can talk about amplification. So the idea is that if you put a small signal current on the base terminal, what you get out on the output, which is a collector terminal, is an amplified version of it. That's the idea. Okay? And of course, in this case, the base collector voltage will give you the bias. It will make sure that the transistor is reverse biased. Okay, we will revisit this soon again. Okay? So keep that picture in mind. And in the configuration that we're interested in doing is what is called the common emitter configuration. Okay? The input goes to the base. Emitter is common to both the circuits. Okay, we'll see an example of that. Okay. So, how does the base current affect the collector current or the output? Okay, that's another way to think about this, again, conceptually. So, the picture is the following. In the ideal case, all the current from emitter to base is holes. So, in the ideal case, we ignore, and we'll formulate the equations in the ideal case first. We ignore this small component of the electron current. We assume that all the current across from the emitter to the base is because of holes. And that can be done if you have a very heavily doped P plus material on the emitter side. Okay? So we assume that everything here is holes, okay, which means that the gamma is 1. This is 1. Okay? 2, there is no reverse saturation current from the collector to the base, which means that we ignore that small current over here, okay, which is typically small, so it can be ignored. It's a reverse bias P junction. Okay? In that case, irrespective of those two assumptions are important for what the equations we'll write down. But irrespective of that, the whole base region, just like any other region in the device, should remain charge neutral. Okay, so you cannot have charges building up or dying down in steady state. Okay, that's the assumption will do. So what that means essentially is that the number of electrons injected in from the base terminal must match the number of holes that exist in the base at any given time. Okay? So if you look at the base, essentially a very thin base, there are electrons coming in, holes coming in. Okay? The number of electrons coming in should match the number of holes coming in. Otherwise, you will lose charge neutrality. The only two things that are happening based on these two assumptions are holes coming in here, electrons coming in here, and holes leaving the place as well. Okay? If you sum all this up, here there should be charge neutral. That's what we'll do. Okay? And that's how we can, another approach to calculate the base current. Okay? So another way to, of course, think about this is that why do the electrons come in? If there is no recombination here, there is no need for electrons coming in. Right? The holes come in, they just leave. So if I were to just draw the base region, I have holes coming in. Okay, this is IEP. Holes leaving here. I'll call it ICP, collector current. And base electrons. Right? If these two are equal, I don't need that. That would be 0. Right? I mean, it would be charge neutral, right? If these two are equal, I have equal number of holes coming in, equal number of holes leaving, and still charge neutral. I don't have any charge buildup. Okay? And that situation is when alpha, right? No, beta is 1. That is the probability that no recombination happens. So if there is no recombination, you don't need any base current. But of course, there's always a little bit of recombination, which is why you need the base current. Right? The difference between this and this is what recombination happens within the base. Holes recombining with electrons, and those electrons have to be provided by the base current. Okay? So one way to calculate the base current is to look at the lifetime of the electrons. Sorry, lifetime of the holes within the base. Okay? So the average time spent by each hole in the base is what's called the transit time. Okay? So it's the velocity of the hole divided length of the base divided by the velocity of the hole. That's the transit time. Right? It's typically less than the lifetime. In other words, you want most of the holes that come in here to go across. You don't want most of them to recombine. Okay, so you want the transit time to be very short, which is why you make the base really thin. Okay. The average time spent by each electron in the base is the lifetime of the hole, because this is the time it takes for the electron that came in to recombine with the hole. So it's the lifetime of the hole. So now you can see what the net charge buildup within this material is. Okay? The electron spends an average of lifetime of the hole inside this base, and the hole spends an average of the transit time within the base. Okay? Which means that now you can estimate the base current, which is only electrons, okay, as a function of the collector current, IC over IB is beta. It can be related to the lifetime of the holes divided by the transit time of the holes. Okay. That's the logic for an amplification for an ideal transistor. So again, if you look at the simple equation, you will see that the average time an electron spends within the base is the lifetime of the hole, because within that time the electron has to recombine with the hole. Okay, that's how it goes in the numerator, tau p. Okay, the transit time is the time that the hole injected from the emitter side spends within the base. Okay, that's tau t. So IC over IB becomes tau p over tau t. So now you can see the amplification factor beta is determined by what? Okay. In order to make the amplification high, what do you need to do? You want the beta to be large. You want a good amplifier. What do you need to do?
Decrease the time it spends.
Yeah, exactly. You want to decrease the time the hole spends in the base, which of course is what we said last class. So it's intuitive, another way to look at it. Right? You want the hole that's injected into the base to essentially make it across into the collector. So you want to make tau t really small. And of course, you also want to make tau p as large as possible, which is the electron in the hole, which means that the base must be of very high quality. You don't want to have any defects in there. So the holes can last a long time. Okay? So that gives you a clue on what is important when actually fabricating these kinds of devices. Okay? Of course, the amplification is not the only thing that's important. So I have an exercise for you now. So I want you to think about, actually, discuss with your neighbor, but think about this picture, okay? Think about the base as a black box. The three things happening: holes coming in from this side, holes leaving on this side, electrons coming in from this side. Now what happens if I start restricting the electrons here? Okay, so discuss for about a minute. It's a little bit of a complicated situation, so think a little bit carefully here. And the hint is that, remember, this is a reverse bias p-n junction, and this is a forward bias p-n junction. Okay, think about it. Okay, remember also it's a PNP device. Okay, it will be different. I should specify that. Okay, so let's think about this problem for a second. So assume this is happening, right? Electron holes coming in, holes leaving, electrons coming in. Now I start to restrict the electrons. What happens? I have fewer electrons coming in. So what do I expect to happen within the base? Think about the base. Go ahead.
Does the equation?
It is related, but let's think even simpler than that. You don't need to think so complicated. Think about the base almost like a black box. Ignore the p-n junctions for now. What happens? You have a charged neutral region here, right? Holes coming in, holes coming out, electrons coming in, everything is balanced. What if I restrict the electrons? Yes, no. That is correct, but why? You jumped one logical step, but that is correct. The answer is correct. Yes, that's correct. Yes, exactly. Yes. So what she pointed out is very, very important, because think about this as a black box, right? There's a charged neutral region. Holes coming in, holes going out, electrons coming in, everything is balanced. Right? The whole thing is charged neutral. Now I'm still talking about steady state. As I restrict the electrons here, there are fewer electrons coming into my black box. So if I don't do anything to these, nothing happens to these currents, what happens? I start building up positive charges within this box. Right? I have all these holes coming in, and I have I have the same number of holes going out, let's say. Fewer electrons coming in, meaning the whole box is getting positively charged now. Right? Excess holes. Not enough electrons to do the recombination. Okay? So now let's put back the junction that he was talking about. We'll see why Mariana, what she said is correct. Okay, so if you look at the p-n junction, so P and P, okay? So remember, this is a forward bias junction, which means that this is positive, this is, okay? More or less, like that. Right? Now, if I'm starting to build up positive charges here, which is what I just said. What does that mean to the bias voltage across the junction? Exactly. Yeah. So when this positive voltages get built up, I'm decreasing the forward bias across the junction essentially. Right? This is almost like reducing the battery voltage. Right? You see that? This is N-type, so if I put positive charges there, that's like decreasing the forward bias. Right? And if I decrease the forward bias, what happens? We know very well from our current voltage characteristics. Not true, but the current looks like that, right? So if I decrease the forward bias, the current goes down, right? Which means my whole injection goes down, which is exactly what you said. So if I restrict the base current, my whole injection has to go down in order to maintain charge neutrality in the base. You see that? In other words, if I treat emitter, collector, base, and I'm only looking at the base, if I send in a small signal to the base, when the signal is less, I have to it will automatically make sure in terms of charge neutrality that the whole injection will correspondingly be less. Okay? And of course that will reflect into the collector current. That will get a nice faithful reproduction of what I put into the base. That's another way to think about it. But it's the same, we're saying the exact same things with three different ways. Okay? So to understand this, again, let me emphasize, to understand the BJT, all you really need to know is the fact that there's a reverse bias junction and there's a forward bias junction giving the reverse, controlling the reverse saturation current. Okay? Okay, so we should now try to quantify, okay, a little bit more than what we had. And let's look at this configuration. As I've said before, the common emitter configuration is the most common way to use the BJT. Okay, and this is what it looks like. So let's walk through it. Common emitter means that the emitter terminal is common to both the circuits, okay, just like we had the base before. The collector is here, base is here. It's a PNP junction, just like what we have been looking at. So again, we have let's look at the reverse bias first, which is let's look at the forward bias first. So this is the base emitter junction is forward bias, because that gives you the whole injection, right? So this has to be positive terminal, that's correct, through some load to the negative terminal, okay? To the N-type, I mean. This junction here must be reverse bias, but it's not obvious from here. It should be. There's no direct connection between them. Okay, it's a common emitter. And we have another circuit over here, which of course is the emitter collector voltage. And it's passed through some load. Okay? So in this situation, what is the control?
The base should be, right? The base current?
Yes, it's still the base current in this situation. It is a base current, it was emitter before. Because the same principle applies, right? This idea that we talked about of restricting and increasing the base current affecting the collector current still applies. The base current is still our control. Okay? Or you can think about this voltage being our control. You can put a small signal voltage on here, which of course will give you a small signal current. Okay, remember it's a forward bias. So this circuit is very easy to understand, right? Because this side is essentially a forward bias PN diode, which means there is no voltage drop. So this circuit, that little circuit right there, is very easy to analyze. Right? You have a 5 volt, you have a resistor, and you essentially have a forward bias diode, right? Which has almost no drop. So this circuit is very easy to understand. This is base, this is emitter. If it is forward bias, of course, if it's reverse bias, it's different. Okay, so we can very easily calculate what the base current should be, Now if I put a small signal instead of a DC, or a DC on top of a small signal on top of a DC, then I know I can put in some signal. Okay, that's my control. Okay. Now, of course, the output, as I said before, is always the collector current, so you should know that. It doesn't matter how you use it, it's IC is the output. Okay. Now, the VCE can be thought of as a bias or an input voltage, and we'll look at that. Okay. Okay, so exercise for you, and I partially answered this. What is the base current in this configuration? Spend about 30 seconds, talk to your neighbors, calculate, and tell me what it is. Should be obvious from what I just said, but by the way, this sort of stuff you should be able to do, because I haven't made the final yet, but I would most likely do something like this. So I'd expect you to know. Exactly. Okay. So I assume it's pretty obvious, right? Everyone's okay with that? So that circuit, to calculate the base current, is essentially what I drew here. Right? And the base emitter voltage, because it's forward biased, is basically zero. Very small drop. So you can very easily calculate the base current of what? Yes, exactly. Okay? Now, of course, if I put a small signal current source or a small signal voltage source here, I can calculate the current. Right? So that's pretty straightforward. Okay, the next question. If the lifetime of the holes is 10 microseconds, the transit time is 0.1 microsecond, what is the collector current? Now, if I'm given these two numbers, what does that mean? That means I'm giving you the base to collector amplification factor, right? IB over IC. Sorry, IC over IB. Is that okay? So what is IC over IB? So again, spend about 30 seconds. Think about it yourself. What is it? Yes. Right? So it's just 100. So what is the collector current? 100 times the base current. Okay? Okay. Does anyone have any questions? You okay with that, Alex? Good? So next question. I want you to think about this carefully. So will this battery or this resistor on the collector emitter circuit affect the collector current? Okay, spend about 30 seconds. Think about that. Okay, we have a battery on that side, and we have a resistor on that side. Okay, what is it there for? One second. Let everyone think a little bit. Okay, we just calculated that the collector current is whatever, right? 100 times the base current. Now, of course, the base current doesn't depend upon whatever I put on the other side. So the answer to the question is, of course, it doesn't. It doesn't matter, right? What I put in there, which is a big advantage. Why? Because that means the output impedance of the circuit is almost infinite. I can put what I want on that side. it'll still give me the same current. Okay, that's a pretty powerful device if you can get something. Of course, in reality, that's not really true. This is the ideal situation, right? But that's essentially a current source, right? It will give you whatever current control current source, right? So think about this second, because it's very important from a circuit perspective. If you ever use these things to design circuits, you really should understand this stuff. Okay? This thing, irrespective of what I put in here, I can put what I want. This is essentially a current controlled current source, irrespective of what I put in here. Right? My collective current, the only thing it depends upon is the base current. Of course, base current depends upon the circuit on the other side, but okay. In the ideal case, the current controlled constant current source with infinite impedance. I mean, everybody sees that, right? So I can put in what I want here, essentially. Pretty much. It's not strictly true. Can someone tell me why it's not strictly true? Yes?
Because the IC that we calculated is essentially the maximum current, but if you don't have a battery to supply, or a power source to supply the load with enough power, then there's not enough power to draw that current through there, right?
That's indirectly correct.
Okay.
But the physics is much simpler than what you're saying.
Okay.
Yeah, go ahead.
So the power supply there, isn't it used to keep the junctions in the correct bias?
Yeah, exactly. Yes.
So if you
Yeah.
put that current high enough, eventually it'll push something out of bias.
That's exactly right.
It's
Yes.
not working.
So again, go back to the simple picture. Okay. So what he's saying was, think about the simple picture. Okay. There are two PN junctions here, and we know PN junctions very well. This PN junction should be reverse biased, right? Remember, if it becomes forward biased, then it doesn't operate like a transistor anymore. We'll look at that in a second. So this must be reverse biased. So of course, this potential plays a role in that. We don't know exactly what yet. But one can imagine, right? This is connected to that, so it must play some role in reverse biasing it. So I cannot put an arbitrarily large negative voltage there, for instance. Okay, I will probably forward bias that junction. Okay, and of course this PN junction must be forward biased. Right? Otherwise I don't have any control of my whole current, whole injection. Okay, so this bias voltage is important to keep the operating conditions at the right location. Other than that, it really does. It's not. But of course that operating condition is very important. Okay. Again, yes, go ahead. Yeah. In the ideal case, right. This is ideal case because, for instance, impedance would matter because if you actually look at a reverse bias junction, this plot, you see, this is actually not completely independent of voltage. There's a small difference. This is my reverse saturation current, which means that the voltage that I apply on this side, in reality, will have some small effect on the collector current. So the impedance is not really infinite. That's the answer. It has a small dependence. In an ideal diode, yes, it's pretty good. Okay. So as a result of this, what we can do is amplification, okay, which is the whole qualitative picture that we're talking about so far. If you put an AC signal to the base current, okay, you can do that by putting a small AC signal to the base bias voltage. Okay, so in a transistor, you can put a little, if you have an analog circuit, communication circuits, whatever, you send in a signal, audio signal, whatever. Okay, that goes in there. What comes out on the collector side would be the amplified version of it. And you can do your signal processing, whatever. Okay, so it's an ideal amplifier, essentially. Of course, you can also use this as a switch. Okay, to use it as a switch is even simpler, right? Because you just need to turn on and off the reverse bias. Okay, as simple as that. Right? Or it's as simple as you can just do zero hole injection, right? And you have zero collector current. Right? Right? If I turn off my hole injection, my collector current is pretty much zero. If I turn on my hole injection, my collector current is high. So I have a 0 and 1 state. I have switching. Okay, switching is a little bit trivial, so we won't necessarily talk too much about it. Okay, so make sure you're very clear on the conceptual picture of what's going on. Okay, and again, we are repeating this many times because this is a little bit subtle, but but you have sufficient background knowledge now to understand it. So keep thinking about that. Okay, now what does the bipolar junction transistor look like when it's fabricated? It's a bit more complicated in the MOSFET because, as you can imagine, there are two different PN junctions which are biased in different ways and so on. The actual device looks like this. Okay, there's an NPN BJT, which is the opposite of what we just saw. Okay, so we start typically with a P-type silicon wafer. Okay, you create an N-type well in the silicon wafer, which is shown here, which is done by implantation. Okay, you take a wafer, you make a little lithographically make a little window in it. We'll talk about that on Thursday. Then you implant some dopant ions into it. In this case, it's N+, so you would put in phosphorus or boron. So you know that now? What would you put in? What's the dopant? Yes. Phosphorus. Right? It will donate the electron. Group 5, group 3, remember? Extra electron 5 has more electrons than carbon. Carbon is 4, silicon is 4. Okay, make sure you're very clear on that too. Now, okay, so you put down, you create a little well, then this serves as a collector. Okay, you can connect it to it with then polysilicon, for instance. It's not a metal, because you want an ohmic contact. Remember, we talked about this for the MOSFET. Okay, this is the polysilicon goes down here, and a metal can go on the very top for the collector contact. Okay, the silicon dioxide separates the collector from everything else. Okay, the collector collects from the base. Now the base is right here, the contact's right here, and that's the base. Okay, this thin region right here forms the transit region for the electrons in this case. So remember, we'll go through the injection in a second, but think about that as the base. Then you have the emitter here. So the emitter in this case is P-type. So, sorry, the base is P-type, the emitter is N+, okay, and is contacted through polysilicon. So what happens? The emitter base junction is forward biased, so let's look at it. Emitter base is forward biased. The electrons come in, it's an N-type emitter, so electrons are the majority carriers. They get injected across this junction, okay, and then you have a very thin base region right there. Okay, so the electrons come across, they will diffuse quickly across to the base. So, sorry, diffuse across to the collector, my mistake, not the base. Base, the holes come in from the base, my mistake. So let's do this again. Okay. Emitter base junction is forward biased. Electrons are injected across the junction into the base, okay, which is this gray region right here. And it will diffuse across to the collector, which is this N+ region down there. Okay, that's your injection current. In this case, electron injection current. Now, of course, the collector current collects that. Now, the base current, what it does is it provides the holes for recombination of the electrons in here, and also for the holes to go across this reverse bias junction. Sorry, this forward bias junction. My mistake. Yes, go ahead.
The fourth contact, I assume, is just another contact for the base.
That's the next emitter. So this is for the next transistor, typically. Okay. So if you look at it, all you need is the collector, base, emitter. This is connected usually in series with the next transistor, which is not shown. Okay? The reason to use electrons versus holes typically is because electrons have higher mobility, lower effective masses. Okay? You can also have what are called bi-CMOS transistors, where you can have the bipolar junction transistors built alongside MOSFETs. In that situation, you can actually envision this kind of a configuration with a MOSFET on the other side, with this being the field stop oxide. Okay? Of course, those are much more expensive to fabricate, and they're very highly specialized chips. These kinds of devices you typically don't find in CPUs and so on. Therefore, specialized chips like sometimes in very fast wireless communication routers, things like that. Sometimes in cell phones. Okay. Okay, so that brings me to this. So the goal for the rest of the class today, so far our idea has been, we've been thinking about this from a very qualitative perspective. Now we want to apply the device as a transistor and look at the transfer characteristics and the input-output characteristics, okay, just like we did for the MOSFET. And that's all really what we need to understand about BJTs. If you're interested in more detail, there's quite a bit more in the text. But from my perspective for the class, I want you to understand the qualitative physics of it and how it's actually used. Those are the two things, okay? So now we'll talk about how it's actually used. So we had the review. The idea, I don't know why this is weird like this, is that, remember what happens, so let me step back. Come back to this picture for a second. So our goal is to be able to quantitatively calculate the collector current as a function of some bias voltages. Okay? So what's going on here is that you have a majority carrier injection. Then those majority carriers become minority carriers in here, and they diffuse and recombine. So you have a diffusion equation here, which is exactly the same as the forward bias injection we did before. Okay, so that's the logic we will apply. And this is the reverse bias, but once the minority carriers reach the junction, they just get swept across by the electric field, the reverse bias electric field. These are minority carriers. Okay, holes in the N-type will get pushed across to the P-type because it's reverse bias. So the only main thing we need to do is solve the diffusion equation here. Okay? And by knowing the recombination current, we can calculate the base current. That's the idea. So in order to do that, of course, we need to know the minority carrier concentration distribution. So of course, for diffusion, we need to know the concentration gradient. Right? We saw this before. We need to know how many injected holes exist, what's the hole diffusion, and what's the reverse bias. Let me see. I think I messed up something here. Okay. Now I remember what this was. Okay. Actually, this is an exercise for you. Look at this PN junction. Okay. This is forward biased. Draw the band diagram under forward bias. So take about 30 seconds. Draw the band diagram forward bias. This exercise is useful because it's exactly what we will use to actually calculate the current for the BJT. So take a simple PN junction. Forward bias it. Draw the band diagram. You should be very comfortable doing that now. Okay, so the p-n junction, the p-type, so valence band, induction band for p-type, the Fermi levels up here. So the n-type, the Fermi levels down here. Your band is just like that, right? That under equilibrium. What happens when you apply forward bias? This is the starting point, not the solution yet.
The bands come
Yes.
together.
Yeah, exactly. Okay. So when you forward bias it, the Fermi level starts doing that. The distance equal to the forward bias, which means that the bands bend less. And what that means is that the energy barrier for the carriers is decreased. So this is p-type. It's more likely that the holes can go that way, because the energy barrier to the holes is decreased. Okay? That's hole injection, or majority carrier injection. Of course, the electrons can also come down, but we try to ignore that for now. Okay? Now, what happens under reverse bias? The Fermi levels move the opposite way. Right? Bands bend even more. The energy barrier increases and the current goes down. Right? It's a basic picture. That's all we need to know to calculate the current. Okay? Is everyone comfortable with that? Okay, you should, I mean, that's the very basic thing in this class. You should be able to do that. Okay, okay. So, now, with that picture in mind, let's look at the bipolar junction transistor. Okay? Like I said, there are only two things to think about. One reverse bias junction, one forward bias junction. Okay, again, the picture is shown here. So you have a base terminal, collector terminal, emitter terminal. The emitter base junction is forward biased. It is this situation right here. Okay? So we can easily calculate what the emitter, whole component of the emitter current is. And there's a whole diffusion here, which we have to solve the diffusion equation, as I said before, with some boundary conditions. Okay? There's only two things we need to worry about in the ideal situation. Hole injection and hole diffusion. Okay? Now, this is a common base configuration, so the base would be the control. Okay? Keep that picture in mind. So, we know from before that when you have a forward bias p-n junction, the concentration of the majority carriers on the other side, where to draw the functional position, the excess hole concentration, of course, it will be very high right at the interface because of the hole injection. And as you move away from the interface, I should have an exponential decrease because of recombination and diffusion. That was the solution to the diffusion equation. Right? We already did this, so I'm not going to do it again. We know that right at the interface, the whole excess hole concentration should be given by an exponential dependent on the forward bias voltage. VEB being the forward bias voltage, emitter base. Okay? So we know this. Pn being the minority carrier concentration under equilibrium in the n-type base. Okay, it's a p-type emitter, n-type base, p-type collector. Okay, now then there's diffusion that happens because of this concentration gradient. You have high concentration holes here, low concentration holes far away. You have diffusion that happens. But in addition to that, you have recombination, and we can solve the diffusion equation We already done that. Okay. But we have another boundary condition that we can solve. We can apply, I mean. Okay. What happens at the base collector junction? That's a reverse biased PN junction. So that's this situation here. Okay. The base is over here. This is the collector. Flipped around. When reverse bias happens, this was on your midterm, I believe. Carrier extraction happens, right? You pull away the minority carriers from one side. Okay? And you have a situation where concentration of holes here, which are the minority carriers here, is now determined by the reverse bias voltage, VCB. Is VCB positive or negative? Collector to base. For a normal operation, it can be whatever, right? But
Positive.
okay. Does anyone else disagree? Okay, so let's step back a second. Think about the collector and base. Is the junction forward biased or reverse biased? It's reverse biased. Okay, so what collector to base voltage? What should be, positive or negative? Okay, what is collector? P-type or N-type? In this case, look at the picture. Yeah, it's P. So what should be the collector to base voltage? Negative. Okay. So it's easy to get confused, but if you're ever confused, just go back and look at the junction. Remember, the collector to base junction must be reverse biased for normal operation. The emitter to base junction must be forward biased for normal operation. Once you keep that picture in mind, everything else can be surmised logically. You don't need to memorize anything. Okay? I want you to be able to do that sort of logic. Fairly straightforward, right? Once you do it a few times. So because the junction is reverse biased, of course you would expect carrier extraction on that side, and the excess hole concentration at that interface should be quite smaller than the equilibrium concentration of holes, right? VCB is negative, so this whole thing, this is very small, right? In other words, this delta PC is negative, which means you have lost holes on that side. Which of course makes sense. It's a reverse bias junction, right? It'll pull those holes out. Okay, carrier extraction, which is what we had in our midterm. Okay. Now we have two boundary conditions. We know what the concentration, excess carrier concentration is at this interface. You know what the excess carrier concentration at this interface. And you know what the diffusion equation is. I'm not going to write it down, but it's a differential equation. Okay? In space. With the carrier concentration as the unknown. You two boundary conditions, you can solve it. You can solve it analytically. I won't go through the solution, but the solution is essentially an exponential. Okay? Of course, a different exponential than when you have just a forward bias junction because you have a new boundary condition on this side. Okay? So go back and think about just the forward bias PN junction that we had, where we assumed a long side, right? We assumed that was pretty long. Then you just had this thing going to zero eventually, at infinity. But now you have a new boundary condition because it's not long, you have another junction there. Okay, so you apply. The solution is pretty much the same. I mean, you get an extra term, but it looks pretty much the same. Okay, and that's the, okay, so this is the diffusion equation, right? How will, we talked about this. This is how the electrons or holes, in this case holes, will diffuse in the N-type material. It includes recombination because you have the diffusion length included there. Okay, we can go back and review that. But if you, so with these three equations, you can solve this. Two boundary conditions and the diffusion equation, you can solve the equation. Okay, you get an expression which looks kind of like this. I mean, you get a distribution which looks like, I don't really care about the expression, don't worry too much about it. But essentially it becomes two exponentials, okay? But don't worry too much. So if you look out here, just concentrate in the middle, which is the base, okay? Okay, this is the excess hole concentration. You have holes, excess holes over here at the interface, very high, like I drew here. And they will quickly diffuse and recombine. And on this end, you have very low. It's negative. It's below its equilibrium concentration because carrier extraction is happening. Okay? That's the only thing we need to know. That's the steady state carrier distribution of holes within the base region. Okay? Everything else is very simple. This side is essentially forward biased PN junction. The electrons got injected across and they diffuse, and this is exactly what we solved before. As long as the emitter is large, it's exactly the same as before. On this side is carrier extraction, which is exactly what you had in your midterm. Okay? In this case, for electrons on the p-type collector. We don't need to worry too much about these two. The only thing we need to worry about is that. Okay? Now, what can we do with this? I mean, our goal, remember, is to calculate the current. If you have a carrier concentration distribution, we can calculate the current. Right? This is the diffusion current. Remember, we broke the PN junction into 4 currents: electron diffusion, hole diffusion, electron drift, hole drift. This is just the whole diffusion current. The drift is very small because there's not much of a field inside, right? It's a neutral region. So you wouldn't expect any big, significant field anyway. Okay. This is the emitter base space charge region, which is the depletion region. This is the base collector space charge region, or the depletion region. Okay. So with that, we can calculate the current. Okay, we can calculate the terminal current. So the first term, like I said, is applying the diffusion equation, diffusion current equation, which is essentially given by minus QA, the diffusion coefficient, times the concentration gradient. Okay, we saw this before. It's a negative sign because it goes down. It's a it goes in from high concentration to low concentration. Okay, we saw this. So applying that, we can calculate it. And it's easy to do. I don't really care about the actual equations so much. You can look it up, but you need to understand where it comes from. If we make the further assumption that the whole injection efficiency is 100%, in other words, that all the current from the emitter side is made up of holes, in other words, this is very small, then we can calculate the emitter current. We can relate the emitter current to the carrier concentration distributions. Okay? So the emitter hole current is now given by some expression here, which depends upon, this is the excess carrier concentration at the interface of the emitter and the base, and this is the excess carrier concentration of the interface between the base and the collector. Okay? And these are essentially, this function is essentially a hyperbolic cotangent, hyperbolic cosecant. They're basically exponential functions, so don't worry too much about them. If you want to, I have a brief thing that shows you the review. But what's important, again, like I said, I don't really care about the equations. What's important is you need to know what this distribution looks like and what that means. Okay? It can be described by these hyperbolic functions. Okay. Now, if we can ignore the reverse saturation current coming from the collector to the base, remember that junction is reverse biased, then we can simply calculate how many holes diffuse across and reach the collector. Okay? Just by solving this equation again on the collector side. Okay? By solving this equation on the base side, on the emitter side is how you get that. By solving this equation on the collector side, or very close to the interface of the collector, you get that expression. It looks the same, pretty much, right? Okay. So this is the collector current, and it's pretty much the same because we ignore recombination. In other words, our assumption here is that all the holes that are injected from the emitter make it across to the collector, mostly because the base is really thin, and they get the same expression. Okay? So that gives you the collector current. Now, the question is, what is the base current? That you should be able to do, right? Okay, Take 30 seconds and tell me what the base current is. Think about this picture. I know what the emitter current is, I know what the collector current is, what's the base current? Yeah. Just apply Kirchhoff's law, right? At that point. Okay. Of course, we should be careful with the directions. Okay. In this case, what is with these directions in mind? What is IP? Yeah. Okay. So, of course, these are slightly different, as I forgot to point out. One is the emitter current and the collector current are slightly different as one would expect. They're not exactly the same. One is a hyperbolic cotangent, and this is a hyperbolic cosecant. Okay, slightly different. But now, what those equations mean, when you put them all together, the base current is now given by IE minus IC. You put them together, you get a fairly straightforward expression. Okay? The hyperbolic functions, again, don't be too scared of it. They're essentially given here. So if you're interested, you can just look it up. They're essentially exponential functions. Right? That's just a simpler way to write it. So the hyperbolic sign is essentially raised to x minus e raised to minus x over 2, and so on and so forth. Everything else follows in an analogous fashion. Yes?
I was trying to figure out what CTN is, and now I'm just like,
Okay. So I would say don't worry too much about it, but if you need to know it, it's here. Okay? It's listed here. Fairly straightforward. Okay. The last part is to understand the BJT as a switch. Okay, we have a few minutes, so we can finish that. Okay. Again, from a more qualitative, it's a quasi-quantitative, let me put it that way. Okay. Simple idea. So, to use it as a switch, again, we go back to the common emitter configuration. Okay. It can be either one, but let's look at this as an example. Okay. So, we have the same circuit here. So, you have a collector, load, battery connected to the emitter, base connected through a load, and some switch to the emitter. Okay. So, now you have a switch here. Plus minus voltage, or plus 0 voltage. Okay, and we want to understand what happens. So the question is, what happens when the voltage goes here from 0 to some 10 volts? Okay. So the first exercise for you to think about, what happens when this voltage is negative, this ES? Just again, think very simply in terms of PN junctions. So look at the base emitter junction. Yes. What does that mean? So first of all, does everybody see that is reverse biased? In other words, if I put a positive, this becomes negative and that becomes positive. That should be forward biased. Wait a second. So my mistake. So I guess I wrote it the same way. But okay, let's follow the logic. So if it's negative, it should be forward biased. Okay, does everyone see that? Yes, right? Okay, because N is connected to the positive terminal, P is connected to the minus terminal in this case. So if the voltage is negative, it's forward biased. And that's normal operation, right? Because you have a forward biased junction between the base and the emitter, you expect injection to happen. Okay, that's okay. So let's look at the opposite situation. When this is positive, of course, analogously, it should be reverse biased. Now, what does that mean when my base emitter junction is reverse biased? No injection. So what happens to the collector current? Yeah, basically be 0. Or very low. Okay, that's my switch. Right? I'm just going from forward bias to reverse bias, and that's my switch. Simple. Okay? I can actually stop there, I guess. But you can look at this in a more complicated manner by looking at what's called the load line. Okay, so if you draw a circuit, if you draw the input-output characteristics of a circuit like this. The output, of course, is the collector current, and the input is the collector-emitter voltage. This is analogous to our MOSFET. Okay, we have curves which look like that, and each of those curves is controlled by the emitter current, which of course is controlled by the switch, whether it's forward biased or reverse biased. So going from a negative voltage to a positive voltage is akin to going from this point here, when it's positive voltage, it's reverse biased, to that point here. Zero current to very large current. Okay? Okay, I think I'll stop here for the time being because I want to make sure we review this on Thursday. And then for the rest of Chapter 7, we will only be talking about the switch. And again, like I said, I want you to know the qualitative explanation of what's going on and very simple quantitative analysis, okay, whatever we covered in class. Don't forget the announcements, okay? Fill out your online survey when you get a chance. It only takes a few minutes. The problem sets are due this Friday. Don't forget the finals. I know people have been asking me, but post it online. Okay? It's next Friday, not this Friday.